So here we are in week 3 already of the bioelectricity course. This is Roger Koch-Barr, the instructor. Thought it would be worthwhile right here at the beginning to see where we are within the course as a whole. We've made plans. We've talked about energy. And now we're into the very core of bioelectricity. There are 3 subjects that we have to talk about. We could talk about them in any order, but I've chosen to talk about them in the order of channels, action potentials, and currents in the tissue structure. So this week our work is about channels. Channels are relatively recently known in bioelectricity. So channels are really the engine that drives the train. They're where the voltages that are created across membranes are converted into currents that actually make things happen. So it is very sensible that our symbol for this week is the train engine, because really channels are the engine that pulls this train. Now, I thought in discussing this topic, we needed to begin by showing the results of some computer simulations of tissue that is passive and tissue that is active. Tissue that is passive when it's passive, that means the channels aren't doing anything special. They're just like holes in plastic or pinholes in any other kind of material. They're there, things flow through, but nothing special happens. It's an ordinary, if still somewhat complex situation. When you go over to active membranes, on the other hand, things are different. And when you look at the simulation, you will see things are definitely different. Whatever you make out of it, whatever the explanation, the difference between passive results and active results, you'll say, wow. Then if you start talking about why does this occur, as we will, you'd say the reason this occurs is because of channels. And when you look at channels, what they're doing, whatever you make out of it, you say, wow. Channels are something that you don't expect to be there like they are. So let's get on with it and look at it look at our schedule a little bit more in detail. So first in the segment 2, we're going to discuss why are passive and active so different. And the first thing to do here is to discuss exactly what the words mean. We're going to use these words over and over, so it's worthwhile to take a little bit of time and rectify the names in the sense of talking about the terminology. So up at the top, I have written the question, why are the passive and active responses to a transmembrane stimulus so different? Let's just talk about the words. A stimulus, this word over here, signified by the pulse symbol over there on the right, is a current that is passed through a patch of membrane. Now the patch of membrane is diagrammatically shown by this box, this green box. So we're thinking of that as a patch of membrane. Inside the membrane, it has a resistance and it has a capacitance. We know that from an earlier week. The capacitance is because it is thin and has a conductor on each side. The resistance is because the membrane has holes. The stimulus is a current stimulus, and we specify the stimulus oftentimes by calling it I-stim, and in this case, the stimulus current is the same as the membrane current. The total current flowing through the membrane is the same as the stimulus current because there's no place else for it to go. You could say the basic out of the stimulus is we take a piece of membrane and we force a current to go through it. The response why are the passive and active responses? So what does the word response mean here? So the response means the voltage. We push a current through the membrane, and what we're asking is, well, what voltage does that create? We're pushing the current across. What voltage does it take to push that current across? Well, voltages develop, and the voltages, you notice, are measured between the inside and the outside of the membrane. Within the membrane, lots of things are happening. We don't know what all those are. We're just measuring the voltage on the inside edge and the outside edge. When we talk about the passive response, that means the response when the tissue is passive, not changing its properties over time. Now, if in comparison, we start talking about the active response, the active response doesn't make anything about the experiment different. It's exactly the same experiment, or in this case, exactly the same computer simulation, except that the tissue itself, our membrane patch, is now active. What that means is that the resistance will change around in its own unique living way to be different resistances at different moments in time. On the other hand, the capacitance, this part, is not going to change. It's going to stay exactly the same because, as you recall, the capacitance comes from the fact of the membrane structure. It has a certain thickness, and it's in contact with conducting solutions on each side. Well, it's worth also talking for a moment about what is meant by so different. The question says, why are the passive and active responses to a transmembrane stimulus so different? So different. So what that says is, what you see as voltages, these voltages are going to be so different for passive tissue and active tissue. Just run through that again. So different. So different. So different. So you're saying, well, how exactly are they so different? Well, you're just going to have to wait and see. But we will before very long. Thank you for watching this segment. I conclude this week I've concluded each of the segments by using some kind of a picture from the North Carolina woods. Here's a tree that's been broken off in a thunderstorm, electric field, high forces. Well, there's that tree. Thank you for watching, and we'll talk again in the next segment.